All right, folks, this section we're going to finish up redox, section 5.5, 5.6 in your textbook. So I'm looking at page 5.18, and now we're back looking at that reaction that's only molecular compounds. There's no ionic compounds. So at first it doesn't look like there are any charges that are changing, but remember we're going to assign these sort of magic oxidation numbers. So I've just got each compound or element on the reactant side, compounds on the right side, and we're going to go through and I assign oxidation numbers. Carbon, hydrogen, and oxygen. Oxygen gets to be -2. There's no other option there. Hydrogen, we know from our other rules, is always +1. Carbon, then, to make that work, now you might want to stop the video for a second. Calculate what the charge, the oxidation number, should be on carbon. All right, you figured it out? And I know that you came up with -2. That's the only way that total charge, remember, is 0. Elements alone are 0. Oxygen here is 0. Over here, oxygen has to be -2. Hydrogen has to be +1. And the only way you can make that work is calculate, pause the video, calculate what the oxidation number should be on carbon. Yep, the only way you can do it, that's got to be 0. Over here, oxygen, most electronegative, -2. Hydrogen, our rules say, are +1. Okay, that's the first step. I have to assign oxidation numbers to each element. What was reduced? Whose charge went down? Well, I look at oxygen here, went down to -2, down to -2. So it looks to me like oxygen was reduced. Whose charge went up? Well, carbon went up from -2 to 0. Now, who reduced oxygen? CH3OH. Right? That was the other reactant. So if carbon got oxidized, it must have been by oxygen. If oxygen got reduced, it must have been by the other reactant. Element was oxidized, O2. So, reducing agent, CH3OH, oxidizing agent, O2. That just sort of brings everything together again in one sample. It's not ionic, there's no ions, there are no charges, so we have to do the pretend oxidation numbers. Let's look at page 5.19. There are a number of examples here. Problem 5.10 is right out of chapter 3. Remember we said we needed to know that? Vanadium is an unpredictable metal, kind of in the middle in the transition metals. We don't know what its charge is going to be, but I know that chloride, each chloride is going to be -1. So what is the oxidation number, the actual ion charge on vanadium? Pause the video, think about that. Yes, of course. It's vanadium 3+ then. So we would say vanadium 3 chloride. I'm not going to do B. I suspect you can figure that one out from that example. Now the answer is in the back of the book, 5.10. That's not blood, by the way. I'm just using all these different colored pens. That's red. Okay, let's look at this. Chromium, we don't know, same problem. Oxygen we know is 2-. Total charge on a compound has to always be 0. So the only way to make that work, chromium oxide, how about chromium 6? I'll do E as well. So you can try D and look at the answer in the back of the book. Nickel, I don't know. Commonly 1 or 2, but I don't know. But I recognize that flashcard from chapter 3. That's sulfate. So this must be 2+. So nickel 2 sulfate. Okay. Chapter 3 review. Remember I said, as promised, it's going to keep coming up. 5.11. I've got some questions here that say, are these redox reactions? The only way to tell is, I don't see any elements alone. The only way to tell is if charges have changed. So I've got to assign oxidation numbers, or the actual charges for ionic compounds. Sodium there, +1. Sulfur, -2. I'm just going back to chapter 3, purely chapter 3. Nickel, don't know. Chlorides, -1. That nickel then must be +2. Now you might pause the video and go to the other side and see if you can do the same trick over there. All right, you got them? Sodium in sodium chloride, +1. Chloride in sodium chloride, -1. Nickel, don't know. Sulfur, -2. So nickel must be +2. How have those charges changed? No change. No. All right, let's do B and C. Let's do B and C. Let's do B and D. Sodium, what's the charge on sodium? Trick question. 0. Element alone. Hydrogen, +1. Oxygen, -2. Remember, those are pretend oxidation numbers. Sodium, +1. Oxygen, hydrogen, -2, +1. Hydrogen, 0. Have any charges changed? Well, I can see a bunch. Sodium got oxidized. Hydrogen got reduced. Yes. It's redox. Let's do D. Carbon monoxide. No ions there. So I'm thinking, well, geez, what is it? Carbon, I don't know. Oxygen gets to pretend it's the anion because it's more electronegative. So carbon must be +2. Oxygen by itself, 0. No charge. Oxygen over here gets to pretend it's an anion. To make that whole thing 0, carbon must be +2. Well, actually, +4. Yep, carbon was oxidized from 2 up to 4. Oxygen's been reduced from 0 down to -2. Yes, that's redox. I'll let you do C and E. The answer's in the back of the book. And this is a little ambitious. If we had more time this semester, wasn't all messed up, we would do that one. You could do it for fun. Well, you know I did it for fun. All right, let's look at page 5.20. More practice. I'm going to do B, B and D, and I'll leave C up to you. So these are the ones we already had assigned numbers to. Oops, let's get that straight. Page 5.20. Sodium was 0, +1. Hydrogen was +1. Oxygen was -2. Now here's something that often confuses students. They say, well, is it +2? No. Oxidation numbers are assigned per atom. So each hydrogen atom is a +1. Over here, hydrogen 0, oxygen -2, hydrogen +1. Whose charge, I'm going to argue, whose charge was reduced? That's the easiest thing. Whose charge declined? Hydrogen started at +1, down to 0. Whose charge went up? Sodium started at 0 and went up to 1. So sodium is the element that was oxidized. Now the thing that was oxidized must have reduced the other thing. So say, oh, the reducing agent was sodium. Itself was oxidized. It must have reduced the other guy. Who oxidized sodium? Well, what was the other reactant? And this is where it gets a little bit weird. H2O. When we talk about what got oxidized and reduced, we talk about individual atoms, individual elements. When we talk about the agents, we say the entire other reactant. So when we say agent, let's see, agent, I should think reactant. All right. I'm going to skip C. I think that one's pretty straightforward. It'd be a good one to practice on. Let's look at D. And here's this wacky one that I was overly enthusiastic. You should do it. It's really fun, believe me. All right, let's see here. Let's look at this one. Carbon over here, we decided, must have been +2, oxygen's -2. So carbon had to pretend it was +2. Oxygen's not pretending at all right here. It's 0. Over here, oxygen, each oxygen atom gets to pretend it's -2, so that carbon atom must pretend it's +4. Who was reduced? Let's see. Oxygen went down to -2. Whose charge went up? Carbon 2 went up to carbon 4. Carbon. Who reduced that? Oh, I just flipped those around. I could fix it. Look, here's my fancy editing. Pretty sweet. I got like 92 billion hits on YouTube already. Okay, let's see. What was oxidized? What was oxidized was carbon, went from 2 up to 4. And what was reduced was oxygen went down from 0 to -2. Well, who reduced the oxygen? The other reactant. Who oxidized carbon? The other reactant. Okay. Go do C on your own. Go look up the answer in the back of the book. If you really have a lot of time, and do that when the answer's in the back of the book. If you have any questions, you can text me or email me, or we can Zoom, and we'll chat about it. All right, last page here in this set is a summary of kind of what we've been doing here. Now let's think about it like this. If we wanted to think about in terms of looking at individual elements now, that we sort of understand the mechanisms maybe. Elements that have low ionization energy, it's very easy to remove an electron. When you remove an electron, do you become positive or negative? Stop the video and think about that. If it's easy to remove an electron, you become positive, right? And the fancy word, you become a cation. That means they want to give away electrons. When they give away electrons, what do they do to the other reactant? If these things are pushing electrons onto somebody else, they reduce their charge. So guess what? Things with low ionization energies want to give away electrons. The thing that receives the electrons, charges drops, it gets reduced. Reducing agents. Where do we find elements that easily give up electrons? Let me get a felt pen for this one. I'm going with the blue. Over here. And even maybe more broadly, all of those metals, right? They like to give up electrons. These really want to give up electrons. When they give up electrons, they reduce somebody else's charge. So we could say these are the reducing agents. Broadly speaking, I suppose we could draw a line there, but these are really strong reducing agents. So we could say something like, oh, sodium, potassium, calcium. All right, now let's flip it the other way around. Where do we find the elements that really want to take electrons? They have high electron affinity. If they take on an electron, they'll become anions because they want to take electrons. If they take electrons from the other reactant, the other reactant's charge goes up. Charges go up, we say oxidize. Oh, atoms with high electron affinity take electrons from somebody else, make their charge go up. So these are good oxidizing agents. Where do we find the really good oxidizing agents? Gee, look at the origin of that word. O2, F2, Cl2, right? So I can say, oh, the good oxidizing agents. Did I get this lined up? Good oxidizing agents. Now I'm looking for a red pen. There's the good oxidizing agents. And that wraps up redox. That's, we had about, 8 or 9, 10 pages of lecture supplement. It's 2 sections in the book, 5.4 and 5.5. That wraps up redox. The next segment is going to be the last part of the book, which is going back to look at net ionic equations again. All right, I'll see you at the next video.